There's a number that appears quietly inside the equations of electromagnetism, quantum mechanics, and relativity. It has no units. It carries no dimension. It does not depend on meters, seconds, or kilograms. It is simply a pure number. Its value is approximately 0.007297355256. Physicists more often write it as 1 divided by 137. This number determines how strongly light interacts with matter. It governs how tightly electrons bind to atoms. It sets the splitting of spectral lines. It influences the structure of chemistry. It even determines corrections to the magnetic moment of the electron measured to extraordinary precision. And yet, despite its central role in physics, no accepted theory predicts why it has this value. This is the fine structure constant. To understand why it is mysterious, we must first understand where it comes from. The constant is usually written as alpha equals E squared divided by 4 pi epsilon 0 h bar c. Every symbol in this expression is fundamental. E is the elementary charge. Epsilon 0 is the permittivity of free space. H bar is the reduced Planck constant, and c is the speed of light. What makes alpha extraordinary is that when these constants combine in precisely this way, all units cancel. Length disappears, time disappears, mass disappears. What remains is a dimensionless number. Dimensionless constants are special in physics. If you change units from meters to feet or seconds to years, their values remain unchanged. They are not artifacts of measurement conventions. They reflect something intrinsic about the structure of the universe. The fine structure constant measures the strength of the electromagnetic interaction. In classical electromagnetism, formulated by James Clerk Maxwell, electric and magnetic fields are continuous waves governed by differential equations. But classical theory does not contain alpha explicitly. The constant emerges only when electromagnetism meets quantum mechanics. When Max Planck introduced the quantum of action in 1900, and when Albert Einstein described light as quantized photons, a new layer of physics began. Soon after, atomic spectra revealed subtle splittings in energy levels that classical physics could not explain. In 1916, Arnold Sommerfeld extended the Bohr model of the atom by including relativistic corrections. These corrections explained the fine splitting of hydrogen spectral lines. The size of that splitting was proportional to alpha squared. That is why it became known as the fine structure constant. The energy levels of hydrogen in the Bohr model depend on the square of the electron charge and inversely on Planck's constant and the speed of light. When these constants combine, alpha naturally appears. In atomic physics, alpha is roughly the ratio between the electron's typical velocity in the ground state of hydrogen and the speed of light. More precisely, the electron's velocity in the lowest Bohr orbit is approximately alpha times c. This means alpha is a measure of how relativistic atomic electrons are. If alpha were larger, electrons in atoms would move faster. If alpha approached 1, electrons would move near the speed of light. Relativistic effects would dominate atomic structure. If alpha were much smaller, electromagnetic attraction would weaken significantly, and atoms would be more diffuse. Already, without invoking philosophy, we see a purely physical question. Why does the electromagnetic coupling strength equal about 1 over 137 rather than, say, 1/10 or 1/1000th? In quantum electrodynamics, the most precise theory ever constructed, alpha appears as the coupling constant in the interaction between electrons and photons. When calculating scattering amplitudes, every electromagnetic vertex contributes a factor proportional to the square root of alpha. The probability of interaction depends on alpha. The predictive success of quantum electrodynamics is extraordinary. Calculations of the electron's anomalous magnetic moment agree with experiment to more than 10 significant figures. These calculations are organized as perturbation series in powers of alpha. The expansion works because alpha is small. If alpha were close to 1, perturbation theory would fail. The mathematical structure of QED would become non-convergent. The smallness of alpha is what makes the theory computationally manageable. But the theory does not explain why alpha has this small value. It takes it as input from experiment. In modern language, alpha is a parameter in the standard model of particle physics. The Standard Model describes three fundamental interactions: electromagnetic, weak, and strong. Each has its own coupling constant. The electromagnetic coupling at low energies corresponds to alpha approximately 1 over 137. However, coupling constants are not actually constant in the strict sense. Due to quantum fluctuations, they run with energy scale. In renormalization group theory, vacuum polarization alters the effective charge observed at different distances. At higher energies, alpha increases slightly. Near the mass of the Z boson, it is closer to 1 over 128. This running is precisely predicted by quantum field theory and experimentally confirmed. Yet even this deeper framework still requires a boundary condition. The value at some reference scale must be specified. No known symmetry fixes its magnitude. No established dynamical mechanism determines it uniquely. The situation becomes even more interesting when we consider unification theories. In grand unified theories, the electromagnetic, weak, and strong couplings converge at extremely high energy, around 10 to the 16 GeV. In certain supersymmetric models, the running couplings meet at a single point. At that unification scale, the electromagnetic coupling is no longer 1 over 137, but closer to about 1 over 25. This suggests that the low energy value of alpha is not fundamental in isolation. It emerges from a renormalization flow. But again, the unified coupling constant itself remains a free parameter. We have shifted the mystery upward in energy, not eliminated it. The fine structure constant also appears in relativistic quantum corrections beyond hydrogen. It governs the Lamb shift, measured with high precision in hydrogen and muonic hydrogen. It enters scattering cross-sections in particle accelerators. It appears in calculations of pair production and vacuum polarization. The fact that such a wide range of phenomena depend on the same dimensionless number is not mysterious in itself. What is mysterious is that no known principle constrains its value to be exactly what we measure. One might ask whether alpha could vary in space or time. Observationally, physicists have searched for variations in alpha by analyzing spectral lines from distant quasars. Because light from those quasars has traveled billions of years, any drift in alpha would imprint subtle shifts in atomic transitions. Current measurements constrain any variation to extremely small limits. Within experimental uncertainty, alpha appears constant across cosmological time. Thus, alpha is stable, universal, precisely measurable, yet unexplained. The fine structure constant also connects classical electron radius, Compton wavelength, and Bohr radius in elegant ratios. The Bohr radius is proportional to h bar squared divided by electron mass times E squared. When expressed in terms of alpha, it becomes inversely proportional to alpha times the Compton wavelength. These geometric relationships suggest that alpha sets the natural scale hierarchy inside atoms. If we imagine gradually increasing alpha while keeping other constants fixed, atomic binding energies would increase. At alpha greater than approximately 0.1, relativistic instabilities begin to appear in heavy nuclei. At alpha approaching 1, atomic structure as we know it collapses. These are not speculative statements, but results derived from relativistic quantum equations. Thus, alpha controls the boundary between stable and unstable atomic matter. Despite all this, when we write down the Lagrangian of quantum electrodynamics, alpha enters simply as a parameter multiplying interaction terms. There is no equation inside QED that outputs 1 over 137. The theory predicts relationships between observables once alpha is specified. It does not derive alpha from deeper mathematics. This places the fine structure constant among a small class of fundamental dimensionless parameters in physics whose values are measured rather than deduced. In quantum electrodynamics, the fine structure constant is more precisely defined in terms of the gauge coupling. The QED Lagrangian density can be written as -1/4 f mu nu plus psi bar times I gamma mu d mu minus m times psi, where d mu equals partial mu plus I e a mu is the covariant derivative. The parameter E is the electric charge appearing in the interaction term psi bar gamma mu a mu psi. The dimensionless coupling constant is defined as alpha equals E squared over 4 pi h bar c. In natural units, h bar equals c equals 1. This simplifies to alpha equals E squared over 4 pi. This formulation makes clear that alpha is directly proportional to the square of the gauge coupling. In perturbation theory, scattering amplitudes expand in powers of E, so cross-sections expand in powers of alpha. However, E is not fixed at all energy scales. Vacuum polarization alters the effective electric charge due to quantum fluctuations. Electron-positron pairs spontaneously appear and disappear in the vacuum. These virtual pairs screen the bare charge. The formalism describing this scale dependence is the renormalization group. The renormalized coupling depends on momentum transfer q squared. At one loop order in QED, the running coupling is approximately alpha of q squared equals alpha of mu squared over 1 minus alpha of mu squared over 3 pi times ln of q squared over mu squared, where mu is the reference renormalization scale. This logarithmic running was derived using renormalization techniques developed in the mid-20th century, formalized by Freeman Dyson and later clarified through renormalization group theory by Kenneth Wilson. The running implies that alpha increases with energy. At very short distances, high momentum transfer, the effective electromagnetic interaction becomes slightly stronger. Experimentally, at the mass of the Z boson, or 91 GeV, alpha to the negative 1 is about 128 rather than 137. This scale dependence demonstrates that alpha is not a fixed microscopic number in the naive sense, it is the low-energy manifestation of deeper high-energy dynamics. Renormalization introduces an important conceptual distinction between bare parameters and renormalized parameters. In quantum field theory, the bare charge appearing in the Lagrangian is not directly observable. It is formally divergent before renormalization. Only the renormalized scale-dependent coupling has physical meaning. Thus, the measured value 1 over 137 corresponds to alpha evaluated at low momentum transfer, essentially the Thomson limit of zero energy scattering. This means the value 1 over 137 is not the coupling at arbitrarily small distances. It is an effective coupling after vacuum screening effects are included. Yet even after accounting for running, the theory still requires boundary input, the value of alpha at some reference scale. Grand unified theories attempt to explain coupling constants by embedding the standard model gauge group SU3 times SU2 times U1 into a larger simple group such as SU5 or SO10. In such frameworks, the three gauge couplings unify at high energy. The renormalization group equations at one loop level are d alpha to the negative 1 over d ln mu equals negative bi over 2 pi, where bi are beta function coefficients determined by particle content. In minimal supersymmetric extensions, the running of couplings converges more precisely. This suggests that at very high energies, around 10 to the 16 GeV, there is a single unified coupling constant. But even if unification occurs, the unified coupling itself is not predicted by the theory. It is a free parameter set by boundary conditions at even higher scales, possibly near the Planck scale. This shifts attention to quantum gravity. At the Planck scale, defined by combining h bar, c, and g, quantum gravitational effects become significant. The Planck energy is approximately 1.22 times 10 to the 19 GeV. Some theoretical approaches attempt to determine coupling constants from Planck scale physics. In string theory, gauge couplings arise from the geometry of extra dimensions. The effective four-dimensional coupling constant depends on compactification volume and shape of extra dimensions. In principle, alpha could be calculated from topological properties of the compact manifold. However, the landscape of possible compactifications is vast. There is no unique prediction for alpha without selecting specific vacuum configurations. In asymptotically safe gravity scenarios, renormalization group flow might approach a non-trivial ultraviolet fixed point. If such a fixed point constrains gauge couplings, alpha could become calculable from consistency conditions. This remains speculative and not experimentally verified. Another avenue concerns charge quantization. Electric charge is observed in discrete multiples of E. The quantization condition can be derived if magnetic monopoles exist. Powell-Dirac showed that the existence of a magnetic monopole implies the quantization condition E times G equals NH bar times C over 2, where G is magnetic charge and N is an integer. This relation implies that electric charge cannot vary continuously. However, it does not determine the magnitude of E itself unless the monopole charge is specified independently. Thus, even charge quantization does not fix alpha. Precision measurements provide additional depth. The most accurate determinations of alpha come from two methods: measurements of the electron anomalous magnetic moment, G-2, and atom recoil experiments using interferometry. The theoretical prediction for the electron G-2 involves high-order Feynman diagram calculations with thousands of diagrams. Agreement between theory and experiment tests QED at extraordinary precision. These calculations confirm that alpha is approximately 1 over 137.035999. The fact that a single dimensionless number must be inserted into such calculations and that all precision results hinge on it emphasizes its central role. Now consider the relationship between alpha and classical scales. The classical electron radius, Re, is defined as Re equals E squared over 4 pi epsilon naught me c squared. The Compton wavelength lambda c is lambda c equals h bar over me c. Taking their ratio, Re over lambda c equals alpha. Thus, alpha is the ratio of classical electron radius to quantum wavelength scale. This relationship reveals that alpha encodes the strength of electromagnetic self-interaction relative to quantum mechanical localization. If alpha were larger, the classical radius would approach the Compton wavelength. This would signal a breakdown of perturbative consistency. This ratio also appears in scattering cross-sections such as the Thomson cross-section. Sigma t equals 8 pi over 3 Re squared. Since Re proportional to alpha, cross-sections scale as alpha squared. Therefore, macroscopic observables like scattering probabilities ultimately depend on alpha. Next, consider bound-state quantum electrodynamics. The Dirac equation for hydrogen yields energy levels En equals mec squared times 1 plus alpha squared over n minus delta J squared to the power of -1/2, where delta J includes relativistic corrections depending on total angular momentum. Fine structure corrections scale as alpha to the 4th mec squared. Hyperfine structure introduces additional factors involving alpha and magnetic moments. Each level of correction introduces higher powers of alpha. This hierarchical structure works precisely because alpha is small. If alpha were not small, the perturbative expansion in alpha would not converge. The Dirac equation solution would not provide stable bound states in the same way we observe. Thus, the existence of stable atomic spectra in the form we observe depends quantitatively on alpha approximately 1 over 137.035999. There is another layer. Quantum electrodynamics exhibits a theoretical pathology known as the Landau pole. At extremely high energies, the running coupling alpha of q squared diverges at a finite scale. Alpha of q squared tends to infinity as q squared tends to lambda L squared. This Landau pole appears far beyond any physically relevant energy, vastly exceeding the Planck scale. Nonetheless, it implies that QED as a standalone theory is not ultraviolet complete. This was analyzed by Lev Landau and collaborators. The presence of a Landau pole suggests that QED must be embedded in a more complete theory at high energies. Thus, alpha is not only unexplained numerically, but its very behavior implies incompleteness of the theory that contains it. We now approach deeper conceptual territory: dimensional transmutation and scale generation. In quantum chromodynamics, CQD, the strong coupling constant runs in the opposite direction. It decreases at high energies, asymptotic freedom, and increases at low energies, generating a dynamical scale, lambda CQD. In QED, no such dynamical scale arises naturally. The smallness of alpha is simply inserted. The contrast between CQD and QED highlights the puzzle. The strong coupling at low energy is of order 1, generated dynamically. The electromagnetic coupling remains small and dimensionless. There's no known mechanism inside QED that dynamically drives alpha toward 1 over 137. The running of the electromagnetic coupling is governed by the beta function. At one loop level in pure QED with a single charged fermion species, the beta function is beta of alpha equals 2 alpha squared over 3 pi. More generally, including NF fermion species of electric charge QF in units of E, the beta function becomes beta of alpha equals 2 alpha squared over 3 pi sigma FQF squared. This equation is derived from vacuum polarization diagrams in which fermion loops modify the photon propagator. The denominator of the photon propagator tensor is d mu nu of q equals minus I g mu nu over q squared times 1 minus pi of q squared. Renormalization absorbs divergences into redefinitions of E and field strengths. The residual finite logarithmic dependence produces running. At higher loop order, additional diagrams contribute, including light-by-light scattering corrections and multi-loop fermionic insertions. These corrections have been computed to very high order, particularly in connection with the electron anomalous magnetic moment. The perturbative expansion of the anomalous magnetic moment is A sub E equals alpha over 2 pi plus C2 times alpha over pi squared plus C3 times alpha over pi cubed plus C4 times alpha over pi to the fourth and so on, where coefficients Cn arise from increasingly complex Feynman diagrams. Thousands of diagrams contribute at fifth order. The agreement between theory and experiment constrains alpha to extraordinary precision, making it one of the best-known constants in physics. This precision highlights an asymmetry. Alpha is measured to extreme accuracy, yet no theory explains its magnitude. Now consider alpha within the east-west sector. The electromagnetic interaction is not fundamental in isolation. It arises after east-west symmetry breaking. The standard model gauge group includes SU2L times U1Y. The electric charge E is related to the weak coupling G and hypercharge coupling G' via E equals G sine theta W equals G' cosine theta W, where theta W is the weak mixing angle. Thus, alpha equals E squared over 4 pi equals G squared sine squared theta W over 4 pi. This expresses alpha in terms of more fundamental gauge couplings and a mixing parameter. The weak mixing angle itself depends on energy scale through renormalization group flow. Therefore, alpha's value at low energies is connected indirectly to the structure of electroweak symmetry breaking. The Higgs mechanism gives masses to W and Z bosons but leaves the photon massless. Gauge invariance under U1EM remains exact. The smallness of alpha compared to the strong coupling constant at low energies reflects the different beta functions of U1, SU2, and SU3. However, nothing in electroweak symmetry breaking uniquely fixes G or G' numerically. They are input parameters. Next, consider non-perturbative aspects. Although QED is perturbative at accessible energies, non-perturbative phenomena such as Schwinger pair production illustrate alpha's role in vacuum instability under strong fields. The critical electric field strength for spontaneous electron-positron pair creation is EC equals ME squared C cubed over EH bar. This scale involves inverse dependence on E. The probability of pair production in a constant electric field contains factors like exponent of negative pi EC over E. The appearance of E in the exponent shows how alpha influences non-perturbative vacuum processes. In intense laser experiments approaching EC, QED effects become nonlinear. The dimensionless parameter governing strong field QED processes is often written as chi proportional to EH bar E over ME to the third C to the fourth, again reflecting electromagnetic coupling strength. Now consider bound state stability constraints from relativistic quantum mechanics. For a point nucleus of charge ZE, the Dirac equation predicts that bound state energy levels remain real only if Z alpha is less than 1. If Z alpha approaches 1, the lowest energy level dives into the negative energy continuum. For alpha approximately 1 over 137, the critical Z would be approximately 137. This suggests that atomic structure becomes unstable for nuclear charge exceeding roughly 137 in a point-like model. Finite nuclear size shifts the exact value slightly higher, but the principle remains. The product Z alpha determines relativistic stability. Thus, alpha sets an upper limit on atomic number for stable Coulombic binding. If alpha were larger, the maximum stable Z would decrease. If alpha were smaller, higher Z elements could exist. This is not philosophical speculation, but direct consequence of solutions to the Dirac equation. In nuclear physics, alpha influences the Coulomb barrier in nuclear fusion and decay. The probability of quantum tunneling through the Coulomb barrier depends exponentially on Z1, Z2 alpha. The Gamow factor governing fusion rates contains exponent of -2 pi Z1, Z2 alpha C over V. Thus, stellar fusion rates depend sensitively on alpha. In early universe nucleosynthesis, reaction rates depend on electromagnetic interaction strength. Variations in alpha would modify primordial element abundances. Astrophysical observations therefore constrain possible deviations in alpha over cosmological time. High-resolution spectroscopy of distant quasars examines absorption lines from intervening gas clouds. The relative spacing of multiplet lines depends on alpha. By comparing laboratory spectra to distant astronomical spectra, limits on variation of alpha over billions of years are obtained. Current constraints limit fractional changes to parts per million or smaller. Theoretical frameworks allowing variation in alpha often introduce scalar fields coupled to electromagnetism. In such models, alpha becomes dynamical. Alpha of phi equals alpha naught F of phi, where phi evolves cosmologically. These models predict violations of equivalence principle and deviations in atomic clock frequencies. Laboratory experiments comparing different atomic transitions over time also constrain alpha variation. Frequency ratios between optical clocks provide sensitivity to alpha because relativistic corrections in heavy atoms scale with Z alpha squared. So far, no confirmed variation has been detected. Next, consider vacuum structure beyond one-loop polarization. The Euler-Heisenberg effective Lagrangian describes nonlinear corrections to classical electromagnetism due to virtual electron loops. L effective equals -1/4 F mu nu plus alpha squared over 90 me to the fourth times F mu nu squared plus 7 times F mu nu F tilde mu nu squared. This shows that photon-photon scattering occurs through higher order effects proportional to alpha squared. Thus, light interacts with light through virtual charged particle loops. The coefficient scaling with alpha squared again reflects electromagnetic coupling strength at quantum level. Photon-photon scattering has been experimentally observed in heavy ion collisions. At even deeper level, consider renormalization scheme dependence. The precise numeric value 1 over 137 refers to alpha defined in the Thomson limit within a specific renormalization scheme, usually on-shell scheme. In modified minimal subtraction (MS-bar) scheme, the coupling at reference scale mu differs slightly. Thus, even the exact decimal expansion depends subtly on renormalization conventions. However, these differences are small and precisely calculable. The essential mystery remains invariant. There is no equation inside the standard model that predicts alpha from first principles. Some speculative attempts relate alpha to geometry or topology. One class of approaches attempts to connect alpha with ratios of volumes in higher dimensional spaces. Another attempts to derive alpha from anomaly cancellation conditions combined with charge quantization constraints. None are experimentally confirmed. Now consider effective field theory perspective. Below electron mass scale, the effective electromagnetic coupling is modified by integrating out heavier charged particles such as muons and tau leptons. Each charged particle species contributes to vacuum polarization. Thus, alpha at low energy contains cumulative contributions from all charged fermions in the universe. In principle, if additional heavy charged particles exist beyond the standard model, they would alter running of alpha at high energies. Precision measurements of alpha therefore constrain possible new physics. At extremely high energies approaching unification scale, threshold corrections from heavy gauge bosons affect matching conditions of couplings. These corrections depend on mass spectrum of heavy particles in grand unified models. Therefore, the low energy value 1 over 137 encodes indirect information about heavy particle physics far beyond current accelerator reach. Quantum electrodynamics can be discretized on a space-time lattice to analyze non-perturbative behavior. In lattice gauge theory, the gauge field is represented by link variables u sub mu of x equals exponent of I a e a mu x, where a is lattice spacing. In compact lattice QED, the action includes plaquette terms S equals beta sigma plaquettes times 1 minus real of UP, where beta is related to inverse coupling, typically beta equals 1 over E squared in appropriate normalization. In this framework, strong coupling and weak coupling regimes can be studied by varying beta. Compact QED exhibits a phase transition between a confined phase and a Coulomb phase depending on coupling strength. For sufficiently large coupling, small beta, Monaco-like excitations on the lattice induce confinement. For small coupling, large beta, the theory resides in a Coulomb phase resembling continuum QED. The physical electromagnetic coupling in nature corresponds to a value deep in the Coulomb phase. This position in parameter space is not determined internally by lattice structure. It must be chosen to match experiment. Non-compact lattice QED avoids monocole artifacts and more directly approximates continuum behavior. In either formulation, alpha is the parameter that sets interaction strength. This lattice viewpoint clarifies that alpha is not emergent from discrete geometry alone. It is a coefficient controlling the weight of field fluctuations. Next, consider renormalization group flow more formally. Define the dimensionless coupling G equals E. In QED, the beta function at one loop is positive. Mu dg by d mu equals g cubed over 12 pi squared sigma f qf squared. Solving this differential equation yields 1 over g squared of mu equals 1 over g squared of mu naught minus 1 over 6 pi squared sigma f qf squared ln of mu over mu naught. Inverting gives the running coupling. The divergence at the Landau pole occurs when denominator vanishes. This pathology implies triviality in the ultraviolet limit. If the cutoff is taken to infinity while maintaining finite renormalized coupling, the bare coupling must vanish. This suggests pure QED cannot exist as a fundamental theory at arbitrarily high energies. The triviality argument was analyzed in detail in renormalization studies by Lev Landau and collaborators. Embedding QED into the electroweak theory avoids this issue because additional gauge interactions modify running at high energies. Now consider the connection between alpha and symmetry principles. Gauge invariance under U1EM dictates the form of interaction but does not fix coupling magnitude. Coupling strength appears as a free parameter multiplying gauge field kinetic normalization. In non-abelian gauge theories, coupling normalization can be partly constrained by group structure, but magnitude remains free. In supersymmetric theories, holomorphy and anomaly cancellation constrain running behavior, but still do not uniquely determine low-energy coupling values without boundary conditions. Next, examine vacuum polarization tensor structure. The one-loop vacuum polarization in dimensional regularization yields pi of q squared equals alpha over 3 pi ln of minus q squared over me squared plus finite terms. This logarithm arises from integrating over virtual fermion loop momenta. Its coefficient is proportional to alpha. The renormalized photon propagator becomes scale-dependent, modifying Coulomb potential at short distances. V of r approximately e squared over 4 pi r times 1 plus alpha over 3 pi ln of 1 over mer plus ... This logarithmic correction is small but measurable in high-precision experiments. Thus, alpha determines both leading-order Coulomb interaction and magnitude of quantum corrections. Now examine multi-loop renormalization structure. Higher-order beta function coefficients depend on renormalization scheme. In QED with NF fermions, two-loop contribution is beta of alpha equals 2 alpha squared over 3 pi plus alpha cubed over 4 pi squared sigma f qf to the fourth plus ... These corrections are numerically small due to small alpha. Perturbation theory remains valid because alpha approximately 0.007 is sufficiently small. If alpha were significantly larger, higher-order terms would become comparable, and predictive control would deteriorate. Now consider bound-state QED beyond hydrogen. In heavy atoms with large Z, relativistic corrections scale as Z alpha squared. Precision spectroscopy of heavy ions tests QED in strong Coulomb fields. For uranium, Z equals 92, Z alpha equals 92 over 137, approximately 0.67. This is still below unity, maintaining relativistic stability, but entering strong field regime. Calculations of energy levels require resummation of Z alpha terms to all orders. The success of such calculations confirms consistency of QED even when coupling effectively approaches order unity in localized region. This shows alpha's smallness globally still allows large effective coupling Z alpha in heavy nuclei. Now consider scattering amplitudes at high energies. The differential cross-section for electron-muon scattering at leading order is d sigma over d omega proportional to alpha squared over S, where S is Mandelstam variable representing squared center of mass energy. Higher-order radiative corrections introduce logarithmic factors ln of S over me squared multiplied by powers of alpha. These logarithms can become large at high energies, requiring resummation techniques such as renormalization group improvement. Thus, alpha governs perturbative expansion, while logarithms encode scale hierarchy. Next, consider vacuum birefringence. In strong magnetic fields, quantum corrections modify propagation of light. The Euler-Heisenberg Lagrangian predicts polarization-dependent refractive indices proportional to alpha squared b squared over me squared. The redshift of recombination depends sensitively on alpha because atomic transition rates depend on it. Cosmic microwave background anisotropy spectra therefore contain implicit dependence on alpha. Precision cosmological data constrain fractional deviations in alpha at recombination to small values. Next, consider black hole physics. Hawking radiation spectrum includes emission of charged particles whose interactions depend on alpha. The gray body factors for charged particle emission depend on electromagnetic coupling. Additionally, charged black holes, Reissner-Strom solutions, have charge Q quantized in units of E. The extremal condition relates mass and charge. M squared is greater than equal to Q squared G over 4 pi epsilon naught C to the fourth. Substituting Q equals NE introduces E into extremal condition. Thus, alpha indirectly influences charge quantization and stability conditions for charged black holes. Now examine vacuum instability in strong fields beyond QED scale. In ultra-intense fields near heavy nuclei or laser pulses, nonlinear Compton scattering and Bright-Wheeler pair production probabilities scale with alpha. Upcoming laser facilities aim to test regimes where multi-poton processes become significant. Theoretical calculations in these regimes use Volkov solutions for electrons in plane wave backgrounds. Transition rates contain factors of alpha multiplied by Bessel functions depending on intensity parameter C equals EE over ME omega. Thus, alpha again sets baseline interaction strength even in extreme regimes. Next, consider renormalization in curved spacetime. In curved backgrounds, effective action for electromagnetic field acquires curvature-dependent corrections. L effect equals -1/4 F mu nu plus alpha over me squared times R F mu nu, etc., where R is curvature scalar. These terms modify photon propagation in strong gravitational fields. Although effects are tiny, they demonstrate coupling between alpha and gravitational curvature through quantum loops. Finally, examine constraints from atomic clock comparisons. Relativistic corrections in heavy elements scale as Z alpha squared. Different atomic transitions have different dependence on alpha. Comparing frequency ratios over time allows detection of tiny fractional changes in alpha. Current experimental limits constrain time variation to parts in 10 to the 17 per year. Thus, across laboratory, astrophysical, cosmological, and high-energy contexts, alpha consistently appears as a universal coupling parameter with extraordinary stability. Consider the concept of asymptotic safety. In a quantum field theory, if the renormalization group flow approaches a non-trivial fixed point at high energies, the theory can remain predictive up to arbitrarily high scales. For QED alone, perturbative analysis suggests no non-trivial ultraviolet fixed point. The Landau pole indicates growth without bound. However, when QED is embedded in a larger interacting system, for example coupled to gravity, the renormalization group equations change. In certain asymptotic safety scenarios for quantum gravity, gravitational fluctuations modify gauge beta functions. Schematically, beta of alpha equals 2 alpha squared divided by 3 pi plus a g alpha plus etc., where g is Newton's constant in dimensionless form and a is model-dependent coefficient. If gravitational contributions introduce a negative term proportional to alpha, a non-trivial fixed point could arise where beta of alpha equals 0. In such a case, alpha would approach a calculable fixed point value in the ultraviolet. This is an active area of theoretical investigation. Results depend sensitively on truncation schemes in functional renormalization equations. No experimentally verified prediction exists yet, but the possibility demonstrates that alpha could in principle be dynamically determined by ultraviolet consistency. Next, consider conformal invariance. Classically, Maxwell's equations in 4 spacetime dimensions are conformally invariant. However, quantum corrections break conformal symmetry through the running of alpha. The trace of the energy-momentum tensor acquires anomaly. T mu mu proportional to beta of alpha F mu nu F mu nu. This trace anomaly shows that even though classical electromagnetism has no intrinsic mass scale, quantum effects introduce logarithmic scale dependence governed by alpha. Thus, alpha controls breaking of scale invariance in quantum electromagnetism. Now consider anomaly cancellation conditions in the full standard model. Gauge anomalies would render the theory inconsistent unless fermion charges satisfy precise relationships. The cancellation of U1Y and mixed anomalies constrains hypercharge assignments. While these constraints fix charge ratios, they do not fix magnitude of E. However, if one considers embedding into grand unified groups, charge normalization becomes tied to group theory factors. For example, in SU5, electric charge operator arises from specific generator combinations. The normalization of U1Y coupling is fixed relative to non-abelian couplings. Thus, alpha at unification scale relates to unified gauge coupling via group theoretic coefficients. Still, the unified coupling remains free parameter unless constrained by additional principles. Next, examine topological effects. In quantum field theory, vacuum angle terms like theta F mu nu, F tilde mu nu are allowed by gauge invariance. For electromagnetism in 4 dimensions, this term is total derivative and does not affect local dynamics in absence of magnetic monopoles. If monopoles exist, the theta term could influence physical observables. Coupling constants and topological parameters can mix under renormalization in extended frameworks. In certain dually transformations, electric and magnetic couplings transform inversely. In n equals 4 supersymmetric gauge theory, S-duality relates strong and weak coupling regimes via a transformation tau minus 1 over tau, where tau equals theta over 2 pi plus I 4 pi over E squared. Such dualities suggest deep mathematical structures relating inverse coupling strengths. Although pure QED does not possess exact S-duality, studying such symmetries in extended theories provides conceptual hints that coupling magnitudes may arise from deeper dual descriptions. Now consider lattice gauge theory with dynamical fermions approaching continuum limit. As lattice spacing A approaches 0, bare coupling must tune to approach renormalized physical coupling. In abelian gauge theory, the continuum limit is achieved in the Coulomb phase at small bare coupling. No dynamic mechanism fixes the renormalized coupling value. Contrast this with non-abelian gauge theories, where asymptotic freedom provides natural ultraviolet behavior. This difference underscores that electromagnetic coupling does not exhibit self-determining scale generation as strong interaction does. Next, examine vacuum polarization from heavy charged particles beyond the standard model. Suppose there exist heavy fermions with mass m and charge q. Their contribution to the running of alpha appears at energy scales above m. Threshold correction at mu approximately m modifies matching condition. Alpha to the minus 1 at mu minus equals alpha to the minus 1 at mu plus minus q squared over 3 pi times the natural logarithm of m squared over mu squared. Precision measurements at different energies can therefore constrain existence of new charged states. Thus, alpha encodes sensitivity to undiscovered heavy particles. Next, move into quantum corrections in bound muonic systems. In muonic hydrogen, electron replaced by muon increases reduced mass dramatically. Binding energy scales as mr alpha squared. Precision spectroscopy of muonic atoms has revealed discrepancies in proton radius measurements. The extraction of proton charge radius depends on theoretical input including alpha. Thus, fine structure constant enters precision determinations of hadronic structure. Now consider renormalization in dimensional regularization more formally. In d equals 4 minus epsilon dimensions, bare coupling E naught relates to renormalized coupling E via E naught equals mu to the epsilon over 2 ZE E. Renormalization constant ZE absorbs divergences appearing as poles in 1 over epsilon. The beta function emerges from requirement that bare coupling be mu independent. Mu d by d mu of E naught equals 0. This leads to renormalization equation governing the running of E and thus alpha. The necessity of introducing arbitrary scale mu demonstrates that alpha is defined relative to chosen scale. Physical observables remain mu independent after including running, but coupling value at a specific scale must be experimentally specified. Now consider quantum corrections to the Coulomb potential in momentum space. Fourier transform of modified photon propagator yields potential v of q squared equals e squared over q squared times 1 minus pi of q squared. Expanding the denominator introduces logarithmic corrections. In coordinate space, this yields Euling potential correction term delta v of r proportional to alpha over r times integral from 1 to infinity of dx times e to the negative 2 merx times 1 plus 1/2 x squared times square root of x squared minus 1 over x squared. This correction has been measured in Lamb shift experiments. Thus, alpha controls vacuum polarization effects at subatomic scales. Next, examine radiative corrections in weak processes. In beta decay, electromagnetic radiative corrections modify decay rates by factors containing alpha over pi. Precision tests of the CKM matrix elements require inclusion of such corrections. Therefore, alpha influences extraction of fundamental weak interaction parameters. Now consider entropy and thermodynamic aspects. In high-temperature plasma, such as early universe or stellar interiors, electromagnetic coupling determines the Debye screening length, lambda d proportional to T over NE squared to the 1/2. Substituting alpha shows screening length depends inversely on square root of alpha. Transport coefficients in plasma, such as electrical conductivity and opacity, contain alpha in denominators or numerators depending on scattering regime. Thus, alpha governs macroscopic plasma behavior across astrophysical scales. Now move to quantum information perspective. Photon-matter interaction strength in cavity QED systems depends on dipole coupling proportional to E. The dimensionless fine structure constant alpha enters spontaneous emission rates via Einstein A coefficient, A proportional to alpha times omega cubed times magnitude of F times R times I squared. Therefore, alpha determines the timescale of radiative transitions in atoms. In ultra-strong coupling regimes in circuit QED, effective coupling ratios approach significant fractions of the transition frequency. Even there, baseline electromagnetic interaction strength originates from alpha. Next, consider effective action in curved backgrounds with strong electromagnetic fields. In strong gravitational and electromagnetic fields combined, vacuum polarization leads to bibirigence and modified dispersion relations.
One-loop effective action includes terms proportional to alpha RF squared over ME squared, linking curvature scalar R and electromagnetic field invariance. Although numerically tiny, these corrections illustrate coupling between quantum electrodynamics and geometry. Now examine renormalization group improvement of effective potential in scalar electrodynamics. In scalar QED, charged scalar field interacts via electromagnetic coupling. Effective potential receives corrections proportional to alpha squared phi to the fourth ln of phi squared over mu squared. This can lead to radiatively induced symmetry breaking, Coleman-Weinberg mechanism. In that mechanism, coupling strength determines whether vacuum expectation value emerges dynamically. Thus, alpha-like couplings can generate mass scales through logarithmic corrections. Finally, consider high-energy scattering at future colliders. At TeV scales, electroweak corrections involve Sudakov logarithms, terms like alpha ln squared of S over mw squared. Resummation of these double logarithms is necessary for accurate predictions. Although alpha's coupling is small, large logarithms can compensate, making higher-order corrections significant. This demonstrates that alpha's influence is not trivial even at high energies where other forces dominate.
In any theory combining quantum mechanics and gravity, additional restrictions emerge on gauge couplings. One proposal, known as the weak gravity conjecture, suggests that in a consistent quantum theory of gravity, gravity must be the weakest force. For a U1 gauge interaction, this implies the existence of at least one particle of charge q and mass m satisfying m less than or equal to q mpl, in natural units where mpl is the reduced Planck mass. Rewriting charge in terms of electric coupling, q equals Ne, the condition becomes m less than or equal to Ne mpl. Since alpha equals E squared over 4 pi I, this inequality indirectly constrains alpha relative to the mass spectrum of charged particles. If alpha were extremely small, electromagnetic repulsion would be too weak compared to gravity, potentially allowing stable extremal black hole remnants that violate entropy bounds. While not yet experimentally verified, such conjectures attempt to tie gauge coupling magnitudes to gravitational consistency. Next, consider black hole thermodynamics more quantitatively. For a charged Reisner-Nordstrom black hole, the extremal condition is gm squared equals q squared over 4 pi epsilon 0 c to the fourth. Expressing q equals Ne and substituting E in terms of alpha gives gm squared equals n squared times 4 pi alpha hc over 4 pi epsilon 0 c to the fourth. This relation shows that alpha influences the mass-charge balance of extremal configurations. If alpha were larger, fewer units of charge would be required to reach extremality. The spectrum of possible stable charged black holes would shift accordingly. Now consider entropy bounds and species counting. In quantum gravity arguments involving black hole entropy, the number of particle species affects ultraviolet cutoff scales. Since each charged species contributes to running of alpha, the measured value of alpha encodes cumulative contributions of all charged degrees of freedom below the cutoff. Thus, alpha is sensitive not only to known particles, but to any undiscovered charged states. If additional heavy charged particles exist near Planck's scale, matching conditions at thresholds would modify high-energy coupling values, potentially altering unification patterns. Next, move into discrete spacetime hypotheses. Some approaches to quantum gravity suggest spacetime may have discrete or combinatorial structure at Planck scale. In such frameworks, effective continuum constants emerge from averaging over microscopic configurations. If electromagnetic coupling arises from expectation values of geometric operators, its magnitude might be determined by underlying combinatorics. For example, in certain loop-based quantization schemes, gauge fields are associated with holonomies around discrete loops. Coupling strength enters as coefficient weighting these holonomies in action. However, no derivation presently yields a specific numeric prediction equal to 1 over 137. Now consider duality between electric and magnetic descriptions. In theories with magnetic monopoles, electric and magnetic couplings are inversely related under dual transformations. E transforms to 4 pi over E. In terms of alpha, alpha transforms to 1 over alpha. Such dualities imply that strong coupling regime of one description corresponds to weak coupling regime of the dual description. Although QED does not exhibit exact self-duality, certain supersymmetric gauge theories do. This mathematical symmetry suggests that coupling magnitude may not be fundamental in isolation, but part of a deeper dual structure. Next, examine the possibility of dimensional transmutation generating alpha-like scales. In non-abelian gauge theories, renormalization group flow generates a dynamical mass scale lambda from dimensionless coupling. In contrast, QED's positive beta function prevents such scale generation in the same way. If hypothetical ultraviolet completion modifies the sign of beta function at high energies, a fixed point could determine alpha dynamically. Functional renormalization group studies explore whether interacting fixed points can exist in abelian gauge theories coupled to matter and gravity. Results depend on truncations and remain inconclusive, but they demonstrate theoretical routes through which alpha might become calculable. Next, shift into cosmological constant interplay. Vacuum energy contributions from charged particle loops scale with alpha times ultraviolet cutoff to the 4th power. Renormalization absorbs divergences, but finite pieces depend on coupling strength. Although cosmological constant problem remains unsolved, electromagnetic coupling influences the magnitude of vacuum fluctuations contributing to vacuum stress energy. Thus, alpha participates indirectly in gravitational dynamics through quantum vacuum contributions. Next, consider renormalization of charge in thermal field theory. At finite temperature T, the screening mass for the photon in a plasma, the Debye mass, is md squared proportional to E squared T squared. Therefore, md squared proportional to 4 pi alpha T squared. In early universe at high temperatures, screening modifies interaction rates and transport coefficients.
Electroweak phase transition dynamics depend on gauge couplings, including electromagnetic component through mixing. Hence, alpha plays role in cosmological evolution of plasma. Now move towards synthesis. Across quantum electrodynamics, electroweak unification, grand unified extensions, lattice discretizations, gravitational conjectures, black hole thermodynamics, cosmological observations, and precision spectroscopy, a single dimensionless number recurs. Its numerical value is inserted into Lagrangians as a parameter. Renormalization group equations describe how it evolves with scale. Symmetry principles determine how it enters interactions. Experiments measure it with extraordinary precision. Yet within currently established frameworks, no derivation fixes its magnitude uniquely. It remains a boundary condition of our physical description. If future ultraviolet complete theories impose fixed point constraints, or if quantum gravity consistency conditions restrict allowable gauge couplings, alpha may eventually be computable rather than measured. Until then, its value, approximately 1 part in 137, stands as empirically determined strength of electromagnetic interaction across all observed scales.